Hello, everybody. Welcome to Module 7, Intro to Networks, Ethernet Switching. My name is Mr. Tandy at Tandy IT. And before we get into Module 7, let's take a look at this quick little video here. Yes, ladies and gentlemen, this is a water park in Southern California in San Dimas area called the Raging Waters. And I'm going to explain what this has to do with any type of networking, internet, all that good stuff. So pay attention really quick as I narrate through this video. So essentially what you're going to see here, okay, I want you to, first things first, this is the Bermuda Triangle. Okay, so let's stop it here. Right now, this person that is in this person, we're going to think this person as a internet packet. Okay, he's an Ethernet frame. And essentially what this person is going to do, he is going to encapsulate himself inside of this tube. We're going to consider this tube as the medium. This could be like a Ethernet cable with a RJ45 connection, a fiber connection, however it may be. So, person is going to enter the Ethernet frame and is going to go into the encapsulation mode. It's going to encapsulate himself into this little tunnel. And at the very, very end, it's going to reach its destination. This is the destination IP, right? Destination IP, different network, things of that nature. So here it is again. Person's going to exit out of here. And there's the decapsulation part, and it re-encapsulates all that good stuff, and it just shows up there. So again, going through it again, when we talk about the data encapsulation. So here it is. This person is going to go through this encapsulation. It's going to encapsulate himself. So this would be like a little packet going through the physical medium. And it wants to reach its source, right? This is the destination IP, which is up here. We can say maybe this is like a 192.168.1.3. And then the water is going to be a .4, right? .4, but that physical medium is going to encapsulate itself through this Ethernet cable. So let's watch it again as it goes through. The data is going through, and then it reaches its source IP, which is going to be the end part here with the water and all that good stuff. Welcome to Module 7, Ethernet Switching. In this module, we're going to explain how Ethernet works in switch networks. We're going to explain how the Ethernet sublayers are related to the frame fields. We're going to talk about MAC addresses. MAC addresses are very important. Describe the Ethernet MAC address, that physical thumbprint that's associated with those devices. We're going to take a look at MAC address tables. I'm going to show you a little packet tracer here on how those MAC address tables build in a switch. And switch speeds and forwarding methods, we're going to describe switch forwarding methods and port settings available in layer 2 ports. Ethernet frames. So the Ethernet encapsulations. Ethernet operates in the data link layer and the physical layers, layers 1 and 2. These are the standards, 802.3, 802.2, okay? It's a family of networking technologies identified by the IEEE standards. This is that Ethernet that comes in. Layer 1, layer 2, right before it gets to the layer 3. This is that encapsulation method here. Data link sublayers, the 802 local area network and metropolitan area network standards include Ethernet uses 2 separate sublayers of the data link layers with the LLC sublayer 802.2 places information in the frame to identify which network layer protocol is used for the frame. And then we have the MAC sublayer, the media access control sublayer, which is 802.3, 802.11, 802.15, which is the Bluetooth here. Responsible for data encapsulation and media access control and provides data link layer addressing. The MAC sublayer is responsible for the data encapsulation and the accessing the media. Data encapsulations, 802.3. Data encapsulations include Ethernet frames. This is the internal structure of the Ethernet frame. Ethernet addressing. The Ethernet frame includes both source and destination MAC address to deliver the Ethernet frame from Ethernet network interface card and the Ethernet network interface card on the same local area network. So very important. As long as they're using the same network, they can address each other. And then error detection, the Ethernet frame includes a frame check sequence, right, to make sure that it is in the proper order. So some of my older videos, we talked about that desk, like that huge desk that gets shipped out. Typically that big desk is not going to go in one big box. Typically it may be in separate boxes, box 1 of 3, 2 of 3, 3 of 3. So as soon as it shows up at its destination, it all gets put back together in its sequence. Media access, IEEE 8023 MAC sublayer includes the specifications for different Ethernet communication standards over various types of media, including copper and fiber. So we talked about this in the last video. This is that Ethernet frame that comes in. Here's the network layer. These are the MAC sublayers as they continue going through the OSI. Legacy Ethernet using a bus topology or hubs is a shared half-duplex medium. Remember the half-duplex. Ethernet over a half-duplex medium uses a contentious-based access method carrier since multiple access collision detection. Remember, that is that, hey, you can go. No, you can't. I can go. It's that four-way stop. You go, I go. I'm going to wait for you to go. What kind of sense to make sure we don't have any detections, any other collisions there on the network. Ethernet local area networks of today uses switches that operate in full duplex. That means everybody on the freeway is moving. We're able to operate. We're able to use our turn signals and go in and out of traffic like we need to. There's no problems there. No problems at all. Ethernet frame fields. Okay, the minimum Ethernet frame fields is 64 bits and the maximum is 1,518 bits. The preamble field is not included when describing the size of the frame. So let's take a look at this frames here, right? We have 64 bytes, excuse me. We have a MAC, destination MAC address, source MAC address, and here's our data, and it is a frame check sequence to make sure that this information is all good. Any frame less than 64 bits in length is considered a collision fragment or a runt frame. So essentially, it's just going to get discarded. If it's not 64 bits, it basically says, who are you? Gotta go. Can't help you here. Frames with more than 1,500 bytes of data are considered jumbo. So it's a big frame. If the size of the transmitted frame is less than the minimum or greater than the maximum, receiving device drops the frame. Drop frames are likely to be the result of collisions or other unwanted signals. So if it can't get there, if there's any other issues, whatever, the information is not going to get there like it needs to. All right, so let's take a look at Wireshark here. So I do have a Wireshark package here. We're going to take a look at a frame here that I was able to capture. Now, obviously, Wireshark is a pretty significant tool that utilizes a lot of the OSI layers. In particular, I have a frame here, and let's see here. We're going to take a look at the Ethernet 2 frame. As you can see here, there is a destination, which is my netgear, because I do have a netgear router. And the source is my source information. It actually gives me my physical address as well. When I click on that, there's my MAC address. And then there's also an IP version 4 protocol. And it gives me my source IP address, which is me asking for the information. And what's the destination? This is the destination IP address, 142.250.184.14. And as it continues, as you can see here, we'll get to the higher ports as we do more of the OSI layer. This is a port 443, so this tells me that I'm having a connection with somewhere on the internet where the session is 443. That is a secure connection. That's the destination port that I was trying to get to, and so on. So once again, here's the Ethernet to the destination, the source, and here's IP version 4. So layer 2s, here's layer 1 as it comes through the wire. Layer 2, the data link as it moves up, and then here's our layer 3, right, as it continues. And we won't get into this. Here's more of the OSI layers as it moves forward. Ethernet MAC addresses. An Ethernet MAC address consists of 48 binary values expressing using 12 hexadecimal values, hexadecimals. Given that 8 bits, 1 byte is common binary grouping binary of 00000 to 11111 can be represented hexadecimal as 00 to FF. So essentially, if all those numbers are off, it's going to get zeros. If all those numbers are on, it's going to get constituted by all Fs, the letter Fs, as in Frank. When using hexadecimal, leading zeros are always displayed incomplete. The 8-bit representation. For example, the binary values of 0001010 represented hexadecimal as 0 and A. Okay. Hexadecimal numbers that are often represented by the value preceding OX, okay, OX73, I'm sure you may have seen those before, is distinguished between decimal and hexadecimal values in documentation. Hexadecimals may also be represented by a subscript 16 or hex numbers followed by H. Now let's take a look at MAC addresses because again, MAC addresses, that's that physical thumbprint of your computer. Okay, your physical thumbprint of that NIC. MAC addresses is an Ethernet local area network. Every network device is connected to the same. Shared media. MAC address provides a method of device identification at the data link layer and of the OSI model. Okay. An Ethernet MAC address is a 48-bit address using 12 hexadecimal digits. Because a byte equals 8, we can also say that the MAC address is 6 bytes in length. Okay. So here is your roll call question. If I'm using a Windows machine, what command would I type in order to find my MAC address using a Windows machine? Send me an email on that. I want to know what that command would be to find your MAC address on the Windows PC. All MAC addresses would be unique to Ethernet devices and Ethernet interface. To ensure this, all vendors that sell Ethernet devices must register with the IEEE to obtain a unique 6 hexadecimal called the Organizational Unique Identifier. So essentially, the first sections of those MAC addresses are all assigned by the organization, right? All assigned by the organization. So the other half essentially will tell you what the vendor gets assigned to. That's that unique code. So to give you just a little bit more of an understanding of how the MAC addresses are used and how the unique identifier and the thumbprint and all that stuff is used by the vendors, I am going to run a ARP-A command on my network. This is essentially what ARP does. Address resolution protocol matches the MAC addresses with the IP addresses. And on my right-hand side here, I do have what's called a MAC lookup app, which I can look up different vendors, all free. So what I'm going to do is I'm going to highlight this MAC address that's associated with this IP address. I'm going to hit Control-C, go over here, Control-V, and I'm going to press Enter. And as you can see, I can tell that the first prefixes, okay, the first half of my MAC address is associated with Amazon. So this is going to tell me that this device that's on my network is some type of a Amazon type of a network. This is also another way to figure out if there are some mischievous things going on your home network, or if there's things that you don't recognize that are in your network, maybe devices that should not be there, things of that nature. ARP-A, looking for your IP address, MAC addresses, you can kind of scan to see which devices are not there. This is why I typically tell a lot of people, most of the time, do not use open networks, especially at Starbucks, things of that nature, because there are people that can get on those open networks and essentially run an ARP command and take a look to see what devices are out there and try to find their way into your device. So we don't want to do that. Frame processing. When a device is forwarding a message to an Ethernet network, the Ethernet header includes a source MAC address and a destination MAC address, right? Source MAC address and destination MAC address, because it needs to know how to get there. When a network interface card receives a Ethernet frame, it examines the destination MAC address to see if it matches the physical MAC address that is stored in the random access memory. That's basically like the MAC table, if it stores information in there. If there's no match, it just throws it away. If it's not there, if it doesn't exist, it just says, have a good day. Not going to be there. Any device, let me go back. Any device that is the source or the destination of the Ethernet frame will have an Ethernet NIC and therefore the MAC address. This includes workstations, servers, printers, mobile devices, and routers. So if it's not a part of it, it'll just kind of say, have a good day. That's just kind of what it is. And this is a good example here. This is not addressed to me, so I shall ignore it. This is not addressed to me, I shall ignore it. This is mine, so it receives the information. In Ethernet, different MAC addresses are used for layer 2, unicast, broadcast, and multicast communication. So when we talked about these in earlier videos, unicast is, me and you, one person, right? Broadcast is, hello, everybody. Can everybody hear me? Multicast is only talking to a few. A unicast MAC address is the unique address that is used when a frame is sent from a single transmission device to a single destination device. The process that a source host uses to determine the destination MAC address associated with IPv4 address is known as, and there it is, Address Resolution Protocol, okay, ARP. Essentially, when something ARPs, it matches the MAC address to the IP address. This sends out a broadcast. It says, hey, who has this MAC address? Please tell this information to this person. The source MAC address must always be in a unicast. Now, an Ethernet broadcast frame is received on an Ethernet broadcast frame is received and processed by every device on the Ethernet LAN. The features of this Ethernet broadcast are as follows. So when you see all of the Fs on, remember those means all of those ones are on, right? They are all on. So that is a full broadcast. Everybody can see that. Everybody's getting the information. It is flooded out to all Ethernet switch ports except the incoming port. It is not forwarded by the router. So here it is. I need to send data to all the hosts on the network. So here's the source host, and it sends out a full broadcast to everybody. Everybody gets the packet. We're going to do a packet tracer here in a minute so I can show you that here. If the encapsulated data is an IPv4 broadcast packet, this means that the packet contains a destination IPv4 address that has all of the ones in the host portion. This numbering is the address means that all hosts on the local network broadcast domain will receive and process the packet. An Ethernet multicast frame is received by the process by a group of devices that belong to the same multicast group. Okay, so multicast, not everybody's going to get it. Only a certain group of people, a certain group of computers will get the information. Makes things on the internet work, makes things on the network work a little bit more effectively. There are other reserved multicast destination MAC addresses for when the encapsulated data is not IP, such as spanning tree protocol. It is flooded out to all Ethernet switch ports except the incoming port unless the switch is configured for multicasting snooping. Because multicast addressing represents a group of addresses sometimes called host group, they can only be used as destination of a packet. The source will always be a unicast address, so it will always be between you and that one other. MAC address tables. A layer 2 Ethernet switch uses layer 2 MAC addresses to make forwarding decisions. It is completely unaware of the data protocol being carried in the data portion of the frame, such as IPv4 packet, an ARP message, or an IPv6. The switch makes its forwarding decisions based solely on the layer 2 Ethernet MAC address. So it's going to send that off. It's going to look at that MAC address and it's going to make its decision. It's going to decide what it wants to do. An Ethernet switch examines its MAC address table to make a forwarding decision for each frame, unlike legacy Ethernet hubs that repeats bits out of ports except the incoming port. Now, Ethernet hubs, you don't really see hubs anymore. Hubs are kind of ancient. Essentially what hubs is, it automatically, every packet that goes through that hub is going to send it out to every device that's connected to it. It's kind of dumb. It kind of bogs everything down. When a switch is turned on, the MAC address table is empty. I'm going to show you a packet tracer on that here shortly. So examine the source MAC address. We're going to learn. Every frame that enters a switch is checked with new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame entered the switch. If the MAC address does not exist, it is added to the table along with the incoming port number. So essentially, if it's something brand new, if it's a brand new thing that comes through, right, it is going to say, hey, I've never seen this before. Let me ink you into my brain, into my memory brain, my random access memory on the computer, right? I'm going to make sure I know who you are. That way I can be more effective moving forward. If the source MAC address does exist, the switch updates and refreshes the timer of the entry. By default, most Ethernet switches keep an entry in the table for 5 minutes. Please note, if the source MAC address table does exist in the table but on a different port, the switch treats this as a new entry. The entry is replaced using the same MAC address but with the more current port number. Switch learning forwarding continued. Find the destination MAC address forward. If the destination MAC address is a unicast address, the switch will look for a match between the destination MAC address of the frame and the entry in the MAC address table. If the destination MAC address is in the table, it will forward the frame out to the specific port. If the destination MAC address is not in the table, the switch will forward the frame out to all ports. So essentially, it kind of sends that broadcast, right? If it's not in there, it says, hey, I need to find it. I need to know where to go. I need to find this information. This is also known as a unicast, one-to-one. If the destination MAC address is a broadcast or multicast, the frame is also flooded out to all ports except the incoming port. As the switch receives a frame from the device, it is able to populate the MAC address table by examining the source MAC address for every frame. When the MAC address table of the switch contains the destination MAC address, it is able to filter the frame and forward out to a single port. So once it knows what you're asking, it keeps that information in the table. That way it knows next time it sees that information, it gets it out a lot quicker, right? All right, so let me show you this packet tracer here. Let's get this going here. All right. So, and we'll go full screen here so I can get myself out of the picture here. Now, I have a switch here. This was in a previous video where I used this star topology. I have the switch hooked up, and right now I'm going to get into the switch here. Now I'm going to show MAC address table, and as you can see, there is nothing in this table. This table is brand spanking new, right? I just fired this thing up. It does not have any information here whatsoever. Now, just for the sake of doing it, just because I want to try to do things a little differently here, what I'm going to do is hook up a console cable to this PC and to this switch. We're going to console into this computer, into the switch. And I just want to use the PC. This is just for me doing things just a little differently, just because we can. All right. So same thing. I'm going to go show MAC address table. Okay. So right now, there's nothing in there. Nothing is being shown at all. There's nothing in there. So what I'm going to do is this. Since I'm using this PC, and let's verify some connections here. Believe this is going to be at 192.168.1. Take note of this MAC address 0002.1786.24. Okay, that's the MAC address of this little server. And I'm going to ping this address. I'm going to ping this computer. So let me go into this computer here, go to command, and I'm going to type in ping 192.168.1.7. So I'm going to send a ping over there. Okay. Now, let's take a look to see what happens here. First things first, we're sending the ping command out. I'm going to hit play. Okay. Now, the first initial ping goes to the switch. Now remember, there's no table in here, so it does not know anything. So take note already. It's already saying ARP, which is exactly what's going to happen. Pay attention. There it goes. So essentially what happens there, it just ARPed to all these ports. Now, these are not connected. That's why you see the red there. That's why it didn't ARP to those devices, because these devices are connected. But essentially what it did, it says, hey, I need to know what IP address is associated with this MAC address. I need you to ARP out. We're going to examine that here in a little bit. You're getting the red X's here because these computers are saying, not me, brother. Get away. Send that file in somewhere else. That's not me. And let's continue. That file server comes back and says, hey, that's me. Let that PC know that that's me. And then that data goes right back to that computer saying, yes, I understand that's you, right? So now that that's done with, let's actually take a look at that ARP table. Let's cancel back in there. Let's see if there's been anything. Let's see if there's anything that has been gathered in looking at our ARP table. So let's close this out. Let's go into terminal. Now, let's look at our MAC table. And voila, ladies and gentlemen, there it is. Now we have a MAC table that has been populated. So the switch actually learned. Here's the switch. This is my destination, right? Communicating on this port. And this is the source. So now if I were to send the ping again, let's try it again. Okay, let me turn the simulation off here. All right. Reset. So now let me send the ping command again. Let's go into my desktop here. Command prompt. We're going to send the ping again. Now watch what the packet does. Now it should send a unicast. And there it goes. There's a little unicast that goes straight to that device because of the MAC table. It learns exactly who it's coming from. It goes back, and it goes back to the request, right? So that's one of the beauties of having a MAC table, how it learns in there, right? It develops that MAC table, so it has a list of items on there. It knows exactly when that first initial packet comes through, it creates that MAC table. It knows exactly who's who. But a broadcast has to be sent out first. Typically, a broadcast would need to be sent out first. Let's get this stuff out of the way here. All right, so we kind of got into that. All right, switching speeds and forwarding methods. Take a look at these items. Switches use, well, I think we just talked about this. This frame forwarding method receives entire frame and computes the CRC, right? It cuts through switching. This frame forwarding method forwards the frame before it entirely received. At a minimum, the destination address of the frame must be read before the frame can be forwarded out. A big advantage of storing forward switching is that it determines if the frame has errors before propagating. When an error is detected in a frame, the switch discards the frame. So that's essentially kind of what we just saw briefly in that little tutorial. You know, it stored the information and it forwarded it out. And cut-through switching, the switch acts upon the data as soon as it is received. Even if the transmission is not complete, the switch buffers just enough of the frame to read the destination MAC address so that it can determine to which port it should forward out the data. Fast forward switching offers the lowest level of latency by immediately forwarding a packet after reading the destination address. Okay, we won't get into all that here because fast forward switching starts forwarding before the entire packet has been received. Okay, the destination NIC cards, faulty packet upon receipt. Fast forwarding switching is the typical cut-through method of switching. So it just makes it so it's a lot faster. And again, we want a lot more efficiency. That's kind of the biggest thing here. Fragment-free switching, a compromise between the high latency and high integrity of stored and forward switching, and low latency and reduced integrity and fast forward. So it's not as powerful, right? Low latency, the integrity of it is not as great, okay? Because most network errors and collisions occur during the first 64 bytes. This ensures that collisions has not occurred before forwarding a switch. An Ethernet switch may use as buffering techniques to store frames before forwarding them or when destination port is busy because of congestion. So we have port-based memory and we have shared memory. Shared memory shared memory deposits all frames into a common memory buffer shared by all switch ports. An amount of buffer memory required by a port is dynamically allocated. The frames in the buffer are dynamically allocated. The frames in the buffer are dynamically linked to the destination port, enabling the packet to be received on one port and then transmitted to another port without moving into a unique queue. So it just makes things move a lot faster. Two of the most common basic settings on a switch, we have full duplex. Again, going back to the highway in my previous video, full duplex, things are able to move on both highways as fast as possible. And again, half duplex, only one end can send connections at a time. Duplex mismatch is one of the most common causes of performance issues. Making sure that the information is correct. I will tell you that you can go into your NIC on your own card, and there should be a setting on there that says auto negotiate. Well, it'll auto negotiate the speed coming in from your network and what's going out. That way, there won't be any collisions, and that's that duplex mismatch. This occurs when one or both ports on the link are reset, and the integration process does not result in both link partners having the same configuration. So it just causes all kind of issues there. Auto MDX connections, this is what I was saying, the auto feature, being able to go in there and to auto negotiate. Is a direct connection between a router and a host requires a crossover connection. Most switch devices now support automatic medium dependent interface crossover. Yes. And that's, on my particular NIC I have on my card, it has an auto mix feature on it where it negotiates it by itself. You don't have to worry about doing all of the things. All right, that's going to conclude Module 7 on Ethernet switching. So if you ever get any time, make sure you go check out Raging Waters too. It's a lot of fun.